నమస్కారం. డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయ విద్యార్థులకు స్వాగతం.
Hello students, we are going to have a video lesson on vectors and vector calculus. The word vector was invented by William Rowan Hamilton as part of the quaternion he developed, in which all the properties of vectors he introduced. Now we see our conventional method of putting the vector notation. In this, the ways of writing vector notation, we will see f is equal to m a is written here. They are capitals A and F, they are the vectors. Now here this is a vector, it makes an angle theta with x axis. So the x component of this vector Ax is equal to a cos theta and y component is Ay is equal to a sin theta. So we will see the vector in this particular method as A, and another angle at the base of the plane x 0 y plane will give you the angle phi. This is called azimuthal angle, this is called radial angle. Using both these things, we will have Ax is equal to a sin theta cos phi, Ay is equal to a sin theta sin phi, and Az is given by a cos theta. Now there are different kinds of vectors. The first one we can think of is a 0 or null vector. 0 vector or null vector means the starting point and ending point of the vector is the same. That means at a simple dot you will have a vector, and that is called 0 vector. And then you will have a unit vector. Unit vector I j k we have already seen, that will be a useful idea. Collinear and parallel vectors. Two vectors, when they are in the same line, they are called collinear, and when they are parallel to each other, they are called parallel vectors. Equal vectors are those things which have the same magnitude and the direction also same, they may be parallel. The other properties of the vectors are addition, and these two are shown subtraction, multiplication. When A is a vector here and B is another vector here, A and B are added, we will see in the diagram A plus B. Similarly, in this A and B are added, we will see the parallelogram method and it call it as A plus B. When A is this one and B is this one, we will have this as A minus B. See the monitor, we will observe the dot product of scalar product of the two vectors can be thought of as the projection of one onto the other direction. So here I is the unit vector of this one vector in the x direction, another I is in the same direction. I dot I means the scalar product of these two, that is equal to 1, and j dot j also is equal to 1, and k dot k also is equal to 1. But if I is taken as a component in the j direction, it is 0. Similarly, j is taken as a component in the k direction, then also it is 0. K is in the component of I direction, then also it is 0. So I dot j is equal to j dot k is equal to k dot I is equal to 0. Now we will see the vector product or the another product called cross product. This cross product is represented in this particular slide. Please look into the monitor. This will give us the vector product. The vector product or cross product is written, it is A cross B, that is equal to A B sin theta. Then A cross B is also equal to minus of B cross A. Now this is A and this is B, we will have A cross B is in the plane of A and B, but the direction is perpendicular to these two, and hence we can also call it as the plane containing this circle will be like this, and the line that the hand shown in the vertical arrow mark is that one, the direction A cross B value. Now A cross B is also represented as A is AXI, AYJ and AZK. This whole bracket is kept as vector A. Similarly, this is the vector B. When you take the cross product, we also know that the I cross I is taken to be 0, j cross j to be taken to be 0, k cross k to be taken to 0. They are the natural rules of the vectors. I cross j is equal to k, I cross k is equal to minus j and j cross k is equal to I. Using these properties, we can write this A cross B in this form of Ax, Ay, Az and Bx, By, Bz in this particular one. A cross B is written as Axi cross Byj plus then Axi cross Bzk, like that the other components also come, but all these things can be kept in the form of a matrix very conveniently. In the matrix, I, j, k are the unit vectors and Ax, Ay, Az are the components, Bx, By, Bz are other components. A cross B is equal to this matrix. Now, we will see some applications of these things. Scalar field is the field which gives us the quantity only. For example, the temperature is a scalar field at a particular location, the value of the temperature. The monitor you see, this is the map of India, you will have various cities and their temperatures are given. So, they will vary from one place to other place, but at the same place the temperature is the same. So, here this particular thing can be understood using the scalar field. For a vector field application, this vector field application gives us in the space is represented by both magnitude and direction. So, here the lines are representing the velocity vectors, wind velocity of our continent or any place on the earth. So, this is represented by that. Similarly, our heat coming from star like sun towards in all other directions can be represented by a hot plasma flow around. If earth is there in the direction of that flow, from the sun towards earth the hot plasma will flow. So, the heat flow also can be represented by a vector field. We will see the vectors in its applications useful for the physics. So, here we will have what is called a magnitude and a direction. In the case of scalar, only magnitude is seen, and in the case of vector both magnitude and direction. We can see, for example, mass of a particular particle is the scalar, length taken in a particular thing is a scalar. Similarly, the time value number of seconds is taken as a scalar, but when a mass of a particle, when the particle is made to move, we will have its displacement, its velocity and its acceleration and its force, all these are vectors. Like that we will have vectors associated with that if there is a direction. So, like that in physics we will have all physical quantities associated with direction. If wind is blowing from southern hemisphere to northern hemisphere, there is a direction. So, hence it is a wind direction, wind velocity is a vector. Now, we will see the monitor and we will try to understand the vector calculus part of it. So, in the monitor we will have vector calculus is associated with what is called a factor called del. We will see a picture of a scientist called Laplace, and this particular thing is called Laplacian, and this Laplacian is also represented by vectorially in this way. This Laplacian represented in the differential equation form, but this is vector equation form. to make it this symbol del inverted triangle is called I d by dx plus j d by dy plus k d by dz. So, this del is operated on a vector A, where A is a vector having I a x plus j, this is a y plus k a z. Hence, this del operated on that is del dot A. This particular thing is called divergence of a vector field. So, we will get the divergence as d by dx of A x, d by dy of A y plus d by dz of A z. This can also be shown with the help of this particular diagram. This diagram shows the arrow marks are towards the center. This is represented by a mass. For example, you take the case of earth, wherever you allow a stone to be left down, it will fall down, it directs towards the center of the earth. So, this central point is the mass, hence this particular one is called gravitational pull towards the center. So, this can be called as convergence. Convergence is the reverse of the divergence. Negative divergence is called convergence. Next, this is the representation of the divergence of A. Monitor shows the representation of the divergence A. A is a vector, vector shows that there is a flow from this end to this end. There is what is called n here, represented by this dot, and m at this dot, and center C is imagined to be at the center of this. So, it is flowing from this end to that end. So, this flow can be either liquid or gas, we call it as a fluid. When fluid is flowing, the flow direction is known to us and it is represented by the value at the center of the phase PQRS. This is the PQRS, and at the point M is equal to the value of Ax at the center plus the increase in magnitude from C to M, that center towards this point. So, this is what we represent by that particular divergence of A. It is being diverged. The flux entering into the rectangular block is equal to the flux leaving from the rectangular block. Hence, the flux can be stated as the dix by dx, day by dy, daz by dz into dx dy dz, and the amount of flux diverging per unit volume is represented by divergence A. This is the divergence A. So, the divergence A is also represented in the monitor as divergence A gives the rate of flow of the fluid at the point per unit volume. Divergence A, if it is positive, the fluid is undergoing expansion, is source of the fluid. If the divergence A is negative, the source, the fluid is undergoing contraction or going into the sink. So, like that, if the divergence is not there, then you call it as a zero divergence. This is also a representation of the divergence. So, this is the positive divergence, this is the negative divergence, this is the zero divergence. Divergence is calculated using this particular problem. If A is equal to I 3x square plus j 5xy square plus k xyz square, find the values of divergence of A at a point 1, 2, 3. Divergence of A, we will use this formula, and in the place of Ax we will keep it, Ay we will keep this, Az we will keep this, and substitute. The differentiation of this is 6x 10xy plus 2xyz. X value are given as 1, y value is given as 2, z value is given as 3. When you put all those things, we will take the value as 38. We will talk about the gradient of a scalar field. Look into the monitor again. The gradient of a scalar field is represented by a vector E. E is equal to minus grad V, where V is a scalar value, it is the potential. E is the electric field, the gradient of this is represented by grad S is equal to del dot S, where grad S is equal to I dou S by dou x plus j dou y by dou S by dou y plus k dou z dou S by dou z. This is represented in the form of a heat transfer. We can also see this gradient in this particular form. I am keeping this particular ball because it is at elevated place compared to this is elevated compared to this point, hence there is a slope or called gradient. This gradient is called gravitational gradient. What will happen? It will fall down like that. So, this is gravitational gradient. Now, we look into the gradient in a different way, that is called the electric gradient. I brought a transformer. This is a transformer having a central point as lowest potential. We will usually call it as 0, and compared to this part is 2 volts above. So, the gradient between these two is 0 to 2 volts. Similarly, 0 to 4 volts, 0 to 6 volts, 0 to 8 volts, 0 to 10 volts, 0 to 12 volts. Like that, these are electrical gradients. We will see in our house also a plug point where 2 holes are there. One is the line, another one is neutral. So, that is the electrical gradient. We have also seen, when we are talking of applications of the gradient in the vectors, the magnetic field gradient can be very easily shown with the help of a magnetometer and a bar magnet. If the bar magnet is brought very nearer, it will be rotating in one direction. As the bar magnet is taking away, the direction will be different because of the decreasing of the magnetic field. The magnetic field vector is increasing, the magnetic field is decreasing. This increasing and decreasing is called the gradient of the magnetic field. Now, electrical gradient can also be shown using this particular 1.5 volts cell. This is the positive, this is the negative. There is a gradient between these two. Now, we will have an application of the gradient. Look into the monitor where we have a small problem for the gravitational potential and gravitational field at that point. We can see this to be calculated using potential V is equal to I x, j y and k z. R is the distance between these 2 points, a Q point and P point, and we will have the masses of these things. Gravitational field is given by, intensity is given by del of minus G m r, m by r. The intensity is equal to, when you differentiate, you will get this particular formula, and substitute these things, you will get a formula in the form of G m into this r by r cube, and here the last term is important to us, that is G m by r square. Hence, we can say that the gravitational field we calculate using the gravitational potential. Next to that, we will have another application of a vector. Its property of that is curl of a vector field. Curl of a vector field is shown in the monitor. If you have a rigid body which is moving around this axis, we will have curl V is equal to del cross V, where V is equal to omega cross r, and omega is again I omega x, I j omega y, k omega z. R is a radius vector I x plus j y plus k z, and curl V is found to be 2 omega, or omega is 1 by 2 of curl V. This can be shown with the help of a problem. Please look into the monitor. We will have the formula here given by a vector A is equal to I into this plus j into this plus k into this, and in this constants A, B, C are there. There is a condition that it is irrotational. When it is rotating, we will have a curl is existing. When it is irrotational, the curl formula curl A is equal to 0. So, curl formula is very simple. Curl A is equal to I j k dou by dou x dou by dou y dou by dou z, and this value is brought here, and we will substitute these things and equate it to 0. We calculate that C is equal to -1, A is equal to 4 and B equal to 2. This is the curl of that particular vector A that we have. Now, we will try to show the curl in a particular action in the monitor, and this is example given as water flowing in a river. We will have water flowing in a river, whenever we have an obstacle it will try to turn itself in rounds. So, this round is whirlpool. Such things are existing. If suppose somebody wants to swim through this, he is pulled by this effect, and this current is available in a conductor, and the magnetic field is also created when a current is made to flow through. So, these are all examples of that. We will see one example with the help of small model that we have here. This is a glass containing little colored liquid. I have put some pieces of white, and when I am rotating this, you will find a whirlpool like thing, a cone like thing, and these things are observed, these particles are observed rotating like that. You can see the cone in that and the particles rotating in the cone. This represents the curl of that particular thing that is moving from the center towards that end. Radius vector is there, as it is rotating, it will have that rotation. So, this is, if you consider this to be similar to a door, this distance is called radius vector. Here we apply force. Suppose we apply force here, the effect will be less. It is r cross f. R cross f is the vector torque acting along this direction. So, this is radius vector r, this is force applied, it is torque will be acting in this direction. So, if you apply force here, it will be easy. If you apply force at lower points, r value will be lesser and the force has to applied in a greater way. So, whenever we have to apply like that, it will be that one. Now, in the conclusion, we will have some applications on the monitor. Please look into the monitor. We have a variety del dot A, when A is a vector, it is equal to 0. We will call it as steady flow, electrostatic field, gravitational field, rotational motion of incompressible fluid. Now, like that we have the vectors and their definition, their properties and their applications into various fields of physics. They are very important in the developments of the physics and associated mathematics also.
మా కార్యక్రమాలపై మీ సూచనలు సలహాలు తెలియచేయండి. మీ సూచనలు సలహాలు తెలియచేయవలసిన మా చిరునామా: డైరెక్టర్, ఆడియో విజువల్ ప్రొడక్షన్ అండ్ రీసెర్చ్ సెంటర్, డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ, ప్రొఫెసర్ జి రామరెడ్డి మార్గ్, రోడ్ నంబర్ 46, జూబ్లీ హిల్స్, హైదరాబాద్ 500003.